All right, good morning, everyone. So continuing a bit in the topic of the muons, I will present today kind of a scheme for simulations to really quantify this muon rescaling that would be needed in the context of the muon puzzle that we call top-down. Um, this kind of analysis can technically be applied to any kind of experiment that have hybrid measurements where the electromagnetic component of extensive showers can be measured independently. But as you will see in this talk, mainly doing this work in the framework of the Pierre Auger Observatory. So many thanks to the collaboration for the help and the support. I invite you to see the talk by Antonella on Wednesday morning regarding the highlights of the observatory. But yeah, it's the framework, but it technically can be applied to other experiments with similar, like TA, for example. So as I said, this analysis is done in the context of the muon deficit that we found in simulations. You see, it's a very dynamic topic. But yeah, what you see here is this already discussed in previous talks, this discrepancy between data and simulations for different experiments. There will be an update this afternoon by Juan Carlos Arteaga. But yeah, the idea of this analysis is to really quantify by how much you would have to rescale the muon component predicted by hadronic interaction models to fit the data. The byproduct of this analysis is also what we call the Sattler-Matthews beta coefficient. So from this toy model of extensive showers, you can where the beta coefficient essentially describes the change in the muon content of those showers as a function of the primary mass. So this is basically what you see here. So you have the logarithm of the mass, you have the logarithm of the average muon content, and this beta coefficient is essentially inscribed in the slope of the trend that you see here. So a measurement of this particular coefficient will help us not only constrain the amount of energy that is carried away by the hadronic component of extensive showers, but it will also tell us how powerful muons are to discriminate between different mass primaries, meaning that a higher beta will lead, for example, in the smaller difference between proton and ion showers, which could be a bit a problem. So I'm sorry, I will have to introduce you or reintroduce you all the things you probably already know, but how extensive showers are measured for given energy and mass of the primary. So again, you know, fluorescence detectors are measuring this electromagnetic component with containing, for example, the calorimetric energy of the shower, but also the depth of maximum development. And as you go to the ground, then you can measure both components, electromagnetic and muonic, by surface detectors, thanks to the lateral distribution that you see here. So the distance to the shower core and the signal in the tanks, for example, in the case of Auger. Yeah, and one of the estimator that we will use in this particular analysis is this S1000, so the signal at 1,000 meters from the shower core, which is a stable estimator compared to different LDF feed certainty on the LDF feed that can be done on this particular distribution. So this quantity is the one that we will be very interested in further slides. So now, yeah, the top-down method is actually a very simple idea. The idea is to take a shower that you have observed, so represented, for example, by those black data points here for the longitudinal profile of your shower, and you will run simulations for any kind of primaries you're interested in, and you will try to find a shower that best match this longitudinal profile. And by doing so, you'll be able to constrain the electromagnetic component and then look into the distribution at the ground of particles and compare the result from your simulations to the actual shower that you've used as an input. And this is actually taken from a paper of Auger 8 years ago on this particular kind of analysis. And so by having the electromagnetic component constrained by the longitudinal profile simulations, then you will know that any kind of discrepancy that you will see at the ground will be caused by the muons. So this is essentially the idea. And how does it translate in an actual simulation scheme and in how the simulations were done here? So we take a an input shower or an observed shower or a mock-up shower, let's say, mock-up data. This is what the analysis is on here. We simulate a connect shower, so 1D shower where there's no information about the particles on the ground. And the idea is to run many of those connect showers and reconstruct them with the auger reconstruction software, and to have in order to obtain the best longitudinal profile that will match the shower that we use as an input. And as we carry on, once we have found this shower, then we can rerun again, but this time a full Monte Carlo simulations in order to have 3D information about the shower itself. And then, of course, obtain the ground signal for further analysis. And so, in this particular analysis that I'm showing here, I'm not working with real hybrid events. I'm working with a mock-up dataset based on Sibyl-Star hadronic model, which was artificially increase the number of muons. You will have actually a talk by Felix Rin on Thursday morning about this model, so stay tuned on this model for this. And the mock-up dataset that we're actually using consists of both proton and ion primaries for energies around 10 to the 19 electron volts and zenith angle below 60 degrees. We also apply some quality cuts on those events to make sure that we have well-measured, well-simulated, reconstructed profiles. And in total, this is approximately the number of showers that we're using, which can at first seem quite low, but since we're running top-down simulations and there are many connect showers that need to be run in order to find a good shower, it's very time-consuming. So we are also limited by this particular factor. And what you see on the right is essentially the scatter plot of the Xmax, reconstructed Xmax of the Sibyl-Star mock-up dataset and of this S1000 estimator that I showed you earlier. So now we start the top-down simulation scheme. So for this particular simulations, we have to consider a different hadronic model, naturally. So we use the Sibyl 2.3D to try and match the Sibyl-Star mock-up dataset. So find showers in Sibyl 2.3D that will match the longitudinal profile of our Sibyl-Star mock-up dataset. We use essentially the same Corsica, low energy hadronic model and detector reconstruction software versions, is just for matter of consistency to run those simulations. And of course, naturally, when you have an input shower, you have a given energy in a given direction. We also use the same parameters. It's really just the same shower, but simulated with a different hadronic model. And then we do a single fluorescence detector reconstructions of those connect showers. And as I said, we run thousands of them, we run a lot of them, and then we reconstruct them, and we basically estimate how well the reconstructed profile matches the one of the input shower that we're trying to match. And this is done by just doing some chi-square analysis on this comparing the two profiles, but also on the reconstructed values like Xmax, calorimetric energy, but also the energy deposited at depth of Xmax. And so by doing so, here I can show you an example where we took our 800 proton mock-up showers and we try to match them with Sibyl 2.3D, also considering a proton primaries for the simulation. And what you see on the left here is a difference between the input Xmax, the Xmax of our input showers to the reconstructed connect Xmax for the best shower that we found for all of those 800 showers. And you see that you actually have quite a good reconstruction here, represented by this mean and very small standard deviation. Likewise, if you look at the ratio of calorimetric energy, you have also quite a good reconstruction within 3%. And if you look also at the ratio of deposited energy, it's even better. It's even better, it's within 1%. So this connect selection is actually working quite well. And as I said, once you have found your best connects, you have to rerun a full Monte Carlo simulation to have information about the ground distributions of particles. So essentially, you just rerun your connects, but this time you activate a full Monte Carlo simulation. Then you do a hybrid reconstruction of all your showers. Oh, thank you. And then you select the best reconstruction exactly based on the same criteria as you did before for connects. I would like to just highlight the fact that when you transition from connects to full Monte Carlo, we actually preserve the simulated longitudinal profile. So it's actually, there's no loss of information here. It's all going quite well. So what I'm showing now on the left is once you've done this full Monte Carlo simulation, you have this S1000 again for your simulated data set, which is represented by this distribution on the left. But what we're interested in it really is the muon signal, not the total signal. I mean, the total signal, of course, but the muon signal is also something we need. So we apply this universal muon parameterization, where essentially it will tell you for your total signal, what is the fraction of the muons as a function of the primary that you're considering, so iron or proton, the hadronic model that you're using, but also the zenith angle of the shower. When you do that, you can retrieve the distribution of your S mu, of your muon signal. And you can do exactly the same. So you see here, it was for my simulation with CBL 2.3D, but you can also do the same with the mock-up dataset because, well, you're working with simulation, so actually it's quite easy to do. And here, this is kind of a summary of the results you get. So you have S1000 as on the first column and S mu on the average values for S1000 and the average values for S mu for the simulations that you just performed with the top-down, and also for the mock-up dataset that you had as an input. Well, since we're working with a mock-up dataset, we can estimate the true muon signal ratio between our input showers and the CBL 2.3D simulations, which is around 1.47. However, in reality, when you work with real hybrid showers, this quantity here, so the average muon signal of your input dataset, you don't know it because you don't have an event by event identification of the primary mass. But thanks to the top-down paradigm, you can actually kind of skip this parameter and instead work with observables that you actually have access to. And this is the equation for the rescaling factor. If you want to see the full derivation on how we obtain this, it's in the backup. But you see that we obtain a ratio that is very, very close to the true one, which means that the top-down simulation, the top-down scheme is working quite well. Naturally, this was what I've showed you so far was for protons, but you can do the same for the iron showers that I have in my that we have in the input dataset. And you see that in this particular case, the true muon signal ratio is 1.45, and then you do the same calculation, and you also obtain 1.47. So a value that's well within the uncertainties of both quantities. As I explained at the very beginning, what is very interesting in this particular kind of analysis is this Heitler-Matthews beta coefficient, which is essentially, again, the slope of the evolution of your muon signal as a function of the primary mass. So for CBL 2.3D, we know that from the top-down simulations, we have this particular trend, this particular behavior, but now we also have our rescaling factors that I just calculated before. We apply them, and we obtain now our rescale CBL 2.3D with beta coefficient that is shown here. And the good thing, again, working with simulations is that you know what's the true trend of CBL star. And if you superimpose the true value of your of CBL star, you see that there's a very, very good agreement between what CBL star intrinsically has and what the top-down retrieves. So yeah, this is really the main plot. So it actually brings me to my conclusion already. So to summarize, this application of the top-down method was used on CBL star hadronic model using CBL 2.3D to try to match the mock-up dataset from CBL star. We see that the average muon signal of CBL star is well recovered once we rescale this CBL 2.3D. And also, as a byproduct, as I said, this Heitler-Matthews coefficient is also retrieved, and yeah, within the uncertainties of the quantities of the models that we have. Now, if I go into the outlook, of course, we're working with proton and iron, but it will be good to extend this particular analysis to intermediate mass primaries like helium and oxygen, which is currently on the way. We also want to implement a probability of an observed shower to have a given primary mass, because naturally, when you're working with real events, you don't know the mass of the event, but you have some probability based on the Xmax, but also on the mass composition measurements that you've done through other techniques. So we want to implement this in order to be able in the future to apply it to real hybrid events. So yeah, that's the end of my talk. Thank you.
Okay. Okay, thank you very much. Questions, comments? We have some online. Yes, go ahead. I don't know who's asking. It's online a hand.
Hello, Professor.
Yes,
I'm
we-
audible to. I want to ask question. Mu plus mu minus ratio will go down or constant if it travels longer distance.
I didn't catch any of this. Can you please repeat?
Mu plus divided by mu minus ratio, whether it will go down as it travels longer distances or it remains constant.
I'm not sure I understand the question.
the muon, the positive to negative muon ratio is the evolution.
Muon ratio basically.
Yeah.
The muon rate.
Between charge positive and negative muon, so it's the evolution.
No, what is the question? I mean,
See, mu
Oh.
plus divided by mu minus ratio is 1.6. Whether it remains constant as it goes down, deeper down, means underground depth from atmosphere, or
I
it
cannot
remains
answer that question.
constant.
I don't know the answer to this question. I'm sorry.
Thank you.
Underground, if I understood it, I don't know.
Yes, sorry.
I'll have a general remark. Both your procedure and to any kind of rescaling procedure. It's actually embarrassing that nobody seems to realize that 10 to 15% of the muon content in our showers comes from the equilibrium component, from the photo production. This contribution has a different energy dependence, different longitudinal lateral distribution. It is simply incorrect to rescale the total muon yield. This should be subtracted because it's not a hadronically produced muons. Equilibrium component is proportional to the electron shower size.
Okay. Thanks. I think we'll take notes of this. Other questions, comments, observations? If not, we thank Kevin again and continue. And we have Juan Carlos Arteaga to talk about again about muons, this time in Cascade.
Perfecto. So good morning, everyone. First of all, thank you very much to the organizer for the opportunity to give this talk. Continuing with this test of hadron interaction models, I'm going to present analysis that we have performed with Cascade Grande using the muons in order to try to put some restrictions to the post-LAC hadron interaction models. So the main objectives of this work are basically okay. Oh, thank you. Oh, no, not working. Not even here. Not moving here. No. Oh, thank you. Oh, sorry for because of that. So the main objectives of this work are basically to estimate the number of muons as a function of the primary energy between 10 PVs up to 10 to the 18 electron volts using the Cascade Grande data as a function of the zenith angle. That is for zenith angle below 40 degrees. And we have compared also this measurement with the predictions of the post-LAC hadron interaction models, which are QS204, post-LAC, and Siebel 2.3D. So the Cascade Grande collaboration is composed by members of Europe and also from Latin America, Germany, Netherlands. We have from Latin America, Mexico, Brazil. You want more information, you can find it over here. So regarding the characteristics of the detector, so Cascade Grande was an air shower, extensive air shower observatory, which was located on the grounds of the KIT in Karlsruhe, Germany. It took data between December 2003 up to November 2012. So it was dedicated to study cosmic rays with energies between 10 to the 15 electron volts up to 10 to the 18 electron volts approximately. So it was a multi-detector system, it was composed of a multi-detector system. The main detector array was Cascade, which was observed over here, which covered a surface of 200 per 200 square meters. Then it was extended by using a larger array, which was called the Grande array, which covered a surface of 0.5 square kilometers. So the Cascade array was composed mainly by scintillator detectors, 252 electromagnetic stations to measure the electromagnetic component, and 192 shielded detector arrays to study the penetrating component. That is the muons, which was located. You can see Cascade over here. The Grande array was mainly composed by 37 plastic scintillator detectors. They were scattered all along the 0.5 square kilometers surface. So the measurements of the electromagnetic component have this energy threshold, and for the case of the muons, the data that we are going to use here has an energy threshold of around 230 MeVs for vertical incidence. So with this array, we were able to measure different observables. For example, the total number of charged particles, that is electron also plus muons, also electrons. We were also able to separate the number of muons. We also get the arrival direction and the core position. There were several research regarding cosmic rays. For example, we studied the energy spectrum. There are several interesting results about the composition, also about the arrival direction of these particles from the sky. There are also information. We got also information about the knee, the iron knee. We look also for the galactic extragalactic transition, and we also perform some tests of hadron interaction models like the one that we are going to present here. So as we are going to study the muon number in extensive showers by using Cascade, I'm going to show you this slide in which we can see basically briefly how the number of muons was estimated. So by using the shielded detector of Cascade, we got a maximum likelihood estimator from which used as input information the number of muons in each Cascade station, and also the lateral distribution function, which we obtained directly from Monte Carlo simulations. By using this information and by using also the lateral distribution function, which was calibrated by using Corsica simulations, we got this estimator for the number of events, number of muons in the shower, event by event. As you can see, for example, from this plot, from a real shower, where you can see the lateral distribution measured by Cascade and the fit by using this maximum likelihood estimator. Now, for this analysis, this is the data sample that we have employed. It was data which was taken between December 2003 up to November 2012, almost all the period observation of Cascade Grande. The effective time was around 1,830 days, and this was the number of selected events, which was around 12 million of events. We applied a set of selection cuts in order to reduce the systematics in this analysis. For example, that were successfully reconstructed only with events with zenith angles below 40 degrees, also events that were reconstructed mainly within a central fiducial area in order to avoid the Punch-Tau effect, and also some effects, border effects that we can see here around the Cascade detector. Also other cuts on the shower muon size and the number of electrons on the lateral shower edge, and we also asked to have more than 11 Grande stations activated during the event to have a good number of events of large energy. Now, For this analysis, we need Monte Carlo simulations. The Monte Carlo simulations that we have used were produced by using Corsica. We also got a simulation for each of these primary nuclei by following this primary energy spectrum. For the low energy hadron interaction model, we use Fluka for hadronic energies below 200 GeVs. And for the case of the high energy hadron interaction models, we use QGA204, EPOS LAC, and Civil 2.3D. Note that we have used QGA204 in order to build a muon correction function, which depends on the shower size, also the core position and the zenith angle, in order to correct our muon data for the systematic bias that we have in the experiment. That is because we know already what is the origin of this bias, and so we can we understand it and we can correct it for our analysis. So by using these Monte Carlo simulations and the set of quality codes that we have applied, these are the thresholds for the maximum trigger and reconstruction efficiency. For the case of the energy, it's in logarithm scale, it's around 7.1. There are some variations depending on this zenith angle and also depending on the hadron interaction model that we are using, as you can see, for example, from this plot about efficiency as a function of the primary scale. And for the case of the muons, we have a sensitivity of around 10 to the 5 approximately. So with that, let me go directly to the description of the analysis. So in Cascade Grande, we don't have a primary estimator, which is independent in order to get the calibration of the primary energy independently. For example, as in the case of Objet, which they have the measurement for the fluorescence detector. So in order to make and estimate the number of muons as a function of the primary energy, what we have done is to apply this technique, which was introduced by Nebo, Decor, and Sugar. And the idea is to compare our muon flux with the one which is predicted by some energy spectra of reference. In principle, it was supposed that all the experiments should measure the same spectrum, the same energy spectrum. So if we compare our measurements of the muon number with the predictions of this reference model of cosmic rays on the energy spectrum and composition, so if we see any difference in that, these differences in the muon number should be ascribed directly to differences or anomalies between the number of muons in the data and also in the Monte Carlo simulations. So by using these differences between the number of muons in the experiment and with the one which is predicted by this reference model of cosmic rays, so we can get a restriction on the relative ratio on the number of muons in the data and also in the Monte Carlo simulations. So we extract this ratio and we apply directly to Monte Carlo simulations. And from here, from this corrected Monte Carlo simulations, which match our data, so we can estimate the number of muons as a function of the primary energy. So we need a reference composition model in order to do this analysis. And for that, we have used for the composition, the global spline fit model from Hamden-Bixby, which you can see over here, which was rescaled with the primary energy of the Pierre Auger Observatory. So we have used this energy scale. So in order to apply directly to our reference composition model. No, so now, in order to extract this factor, the ratio between the experiment and also the Monte Carlo muon ratio, we have done these following steps. First of all, we correct for the systematic bias. Then we divide the data into zenith angle intervals. Now we compare by using the chi-square method, the corresponding muon histogram, the experimental one, versus the corrected, the prediction of the hadron interaction models for the muon histogram after applying this correction factor. So this is in the logarithm scale that give you the ratio between the experiment and the Monte Carlo. So once that you extract this quantity by using this chi-square method, so you can apply directly to your Monte Carlo simulations, and hence this give you a better description from the data, so that can be already used to calculate the actual muon number. So then the idea is to obtain this quantity, the difference between the experiment and the Monte Carlo simulation, apply to your Monte Carlo data, and this modified Monte Carlo data gives you directly the number of muons as a function of the primary energy. So this is the result of one of the examples of the fit. For the case of the experiment, with the QJ204 data that is for vertical, for vertical events. So we have parameterized this ratio between experiment and the Monte Carlo data by using the second order polynomial. It's very simple. So this is the data before the fit, and this is the result after the fit. So you can see the data points. These are the experiment, and the fit is represented by these red data points. And this is the result of the corresponding fit to the experimental data. So by calibrating this quantity for each of these hadron iteration models, so we obtain our estimation for the number of muons. We have taken into account for statistical and systematic errors, for example, the error on the fitted parameters, the composition, the differences, the lateral distribution functions, the energy scale, and also the mean correction function that we have employed in order to calculate this quantity. These are the results. Here in the first column, in each column, you can see the result for vertical and also for incliner showers. And each of the row, you can see the results for each of these hadron interaction models. Here on the top, you can see EPOS-LAC, then Civil 2.3D, and here QJ204. What can we see over here? First of all, the logarithm of the number of muons over the primary energy as a function of the logarithm of the primary energy. The first thing that we can see is that we cannot see muon excess in the Cascade Grande muon data. We also observe that for the case of vertical air showers, very close to 10 to the 18 electron volts, the hadron iteration models, EPOS-LAC and Civil 2.3D seems to be overestimating our data. But if you go to high zenith angles, it seems that in this case, for incliner showers up to 40 degrees, the data seems to be in better agreement with the predictions of the hadron iteration models for proton and also for iron, as you can see over here. So you can see a reasonable agreement for higher inclinations. We also see that the data has a smaller attenuation with atmosphere, as in the case of the hadron iteration models. This is in line with some previous analysis that we have done with the muon attenuation length. So this is a summary of the results. So here with the data points, you can see the average all of the results. And here with these small dotted lines, you can see the differences by using the different hadronic interaction models to stack the muon data as a function of the primary energy. So you can see that the variations are pretty small. So there is a very good agreement in all the results, independently of the hadron iteration model that we are using in order to stack the muon number as a function of the primary energy. If you compare the data with the prediction of the hadron iteration models, again, you see that the post-LAC models seems to be overestimating our data very close to 10 to the 18 electron volts, and seems to be a better agreement for more incliner showers. Finally, to end, here is a calculation of the statistical and systematic errors. You can see over here that the larger systematic error come directly from the energy scale over here, and also from the uncertainties in the lateral distribution function. But there is no too much dependence on the mass composition and also on the muon correction function, as you can see from here, from this data. So this is the summary. So basically, we have not found muon excess in the Cascade Grande data. So what we have found is that the post-LAC hadron interaction models, EPOS-LAC and Civil 2.3D, seems to be overestimating our data close to 10 to the 18 electron volts for vertical air showers. We are also observing that there is a better agreement for the case of incliner showers within the data and also the Monte Carlo simulations. And there are more work in progress. For example, we are going to study the muon densities as a function of the energy, for also for different distance to the shower core. So thank you very much.
Okay. Thank you very much, Juan Carlos, for the interesting talk. Questions, comments? No questions here? Okay, sorry.
Well, just should comment.
Yes.
There seems to be some qualitatively same trend from stock measurement of muons and from Cascade, right?
From what student?
We had a talk of stock today. The And now we have lack of cascada in both experiments. One doesn't see any
Okay.
any
Yes.
muon excess in the data. Actually, the energy range is also similar, right?
Mhm.
All the two experiments.
Ralph?
Juan Carlos, so thanks a lot. You showed a lot of things here. And so I'm not sure that I really understand how you link this to an external flux, because a GSF model, for example, recalibrates all the experiments. Does it mean you have a recalibration automatically taken care of the energy in the comparison? And what would happen if you choose a different flux model?
If you use, for example, a different energy scale, so your estimation will move depending where you put the corresponding energy scale. So here you, for example, you can see here what happened if you put it, you use another energy scale of which is about 10%. So it will go down your estimation, and you use another energy scale which is a little bit lower. So you will get here that your data will move higher to this position over here.
Yeah, but I'm not really understanding how you do this energy scale here. Why? So initially, so you are linked to one flux model, and there are
Yes.
lots of different flux models available.
Yes.
So it's not clear to me where you get this absolute scale. I mean, we aren't really sure what the flux is. At least this is what I thought. Yeah.
Yes.
And so isn't then your result specific to the GSF model, or?
No. The GSS model is just to have the corresponding composition of cosmic rays.
Mhm.
So even though the result doesn't depend too much of that. We use the restriction from Cascade Grande, you move the composition, the results are almost the same. So it has not a big impact on the results. Now, once that you have this, you can shift it in order to have an energy spectrum, to calibrate your energy spectrum with the one which you want. For example, here we have used the Pierre Observatory, which have some measurements between 10 to the 17 electron volts up to 10 to the 18 electron volts. And we can make some comparisons in this energy range. Where can we put the energy of reference? So in order to do that, we have shifted the GSF model in order to have a match with the energy spectrum around 10 to the 16 electron volts, where you see this low energy angle. So you have this point as a reference, and you use this energy scale, so you can calculate now your corresponding muon histograms to make the corresponding comparison with your data.
Yeah, but it's a very large shift, right? That you apply. So it's not obvious to me that whether that's justified. You know, that let's say if Auger was claiming the energy scale was really correct and
Yes.
rock solid,
Mhm.
then the shift is not going to justify, right?
If that is not correct, so it
No,
will
but-
move then your result.
Okay, okay, this is, I only wanted to say that there is something in this analysis that is so, well, we still have to understand more of it, yeah.
Yes. Just we assume we want to compare with one experiment, so we need to use that energy scale. In this case, we want to
That is,
compare
of
with
course,
OJ, we
definitely.
use this energy scale.
Definitely a good approach, yeah.
Mhm.
Yeah, I agree. Okay, thanks.
Okay. Next, other questions, comments, questions online? Okay, if not. Okay, I think we can finish the session here. Eduardo, you wanted to say something? Anyway, I use that moment also to thank Juan Carlos again and all the speakers of the first session this morning. And now, Eduardo, what is?
Yes. Quick announcement is exactly. Yes, it's about the public lecture on Thursday by Professor Samuel Ting. Is going to be online in this hall. There will be two places. One is outside the hotel in Nuevo Vallarta, and the other is here simultaneously. So after this public talk is the dinner. So you don't need to move to other place, but to stay here. And here you can see the public talk from Professor Ting about encounters with modern physics. So of course, you are very welcome. And after that, in few hours, I hope, I'm going to say in which place of this hotel is going to be the dinner. It's only one, the only announcement. And yes, thank you, Lucas. So coffee break or?
Okay, yes, I guess it's coffee break. You tell us when we resume. We're about 15 minutes late, so I assume we will need to extend the coffee break a little bit for the colleagues here to recharge. So, but I leave it up to you to call us back to the session afterwards.
The next chairman is. Thank you very much, Lucas.
Yeah, thanks.